Hello, fellow humans. Welcome back to outer space and our discussion of BLAST. This is the second of two short lectures on BLAST. The last one we focused on just how it works. And on this one, I'm going to talk a little bit about the scores and the statistics and what you might need to know or want to know if you're running this as a bioinformatician. So to get started, I'm going to share my screen with the slides. Again, these slides are all available on Google Drive. That link again is on our eCampus class page. So sequence alignment using BLAST. Just as a reminder of what we talked about in the last lecture, here's our BLAST summary. We start by seeding with, in this case, 3-letter word neighborhoods. We extend those neighborhoods, we find what are called high scoring, high segment pairs. And then we can combine those into full alignments. Just to note, you can tweak word size, and you can tweak the neighborhood threshold. If you're unsure about what these mean, go back to the first lecture on BLAST. Word size, if you turn it up, so you have longer words, say 4-letter, 5-letter, 6-letter words, the speed of your searches increases quite dramatically because you're pulling out fewer matches, fewer seeds, and you have to go through this seed extension merge combination fewer times. But your sensitivity will go down because for the same exact reason, you're pulling out fewer exact matches or near exact matches. Neighborhood threshold, again, if you turn up the neighborhood threshold, you pull fewer neighborhood words, so your score threshold goes up for that neighborhood. There are fewer 3, 4, 5-letter words in your neighborhood. As a result, the seed number goes down and your speed goes up, but again, your sensitivity will go down. So you can tweak these depending on how sensitive you want your BLAST run and how fast you want it to run. These are generally not changed by many people. Okay, let's move ahead and talk about the scores. When you run a BLAST, you get a bunch of scores back. Max score, total score, query coverage, e-value, identity. Those are the scores that you get. We're going to ignore the difference between max score and total score for now. Query coverage is simply the percent of your query sequence that is included in the alignment. So in this particular case, the top 2 matches here, they are 100% query coverage, which means your entire query was found in this alignment. E-value we're going to talk about in a minute, and then percent identity is also fairly straightforward. That is the percent of residues or bases that are identical, not similar, but identical. So here in this top match, you can immediately see that over the full length of your query, it is 93% identical to this particular protein or this particular sequence. That gives you some very valuable information. Other valuable information is encoded in the scores and the e-values. So these scores, when you run an alignment, as we've talked about, you can calculate an alignment score. And we've also discussed where those scores come from using BLOSSOM or PAM matrices or other matrices, depending on your preference. You can generate scores. Those scores need to be normalized before anything else happens. Normalization of scores, we're calling them bit scores here. Normalization of bit scores allows us to compare sequence search results. The NCBI website explains this as when you get an alignment score back, its score, if you haven't normalized it, is somewhat like trying to compare distances without knowing the units. So 3 versus 4, is it 3 meters? Is it 3 inches? Is it 3 feet? So normalization allows us to standardize the units, regardless of what those actual units are. It also allows comparison between different searches. In order to normalize our raw scores into normalized bit scores, We run this calculation. Again, this is all done for you by BLAST, so it's giving you normalized scores here. We're just walking through how we get those normalized scores. They are a consequence of the database you're searching, so this kappa here and this lambda are database parameters. If you look down the very bottom of a BLAST result, you can often see those parameters calculated for you. Okay, so this is normalization. Again, we're walking through this as simply an exercise. You never have to do the normalization yourself. It's important to note, however, that normalization doesn't indicate significance. You can see that these scores here are high. These top 2 hits in our BLAST result have very high scores compared to, say, the 3rd, 4th, and 5th hits. But what does that difference mean? It's 1,000 score units, but we really have no good understanding of how significant that is. The significance is tied up in the expect value. Now, we can calculate significance in several ways. The way that we calculate it in BLAST is by comparing it to a random occurrence. So we need a model of random amino acid sequences, at least as far as protein alignments go, or nucleotides as far as DNA, RNA alignments go. So the expected value here, the E value here, is what we expect to find compared to a random search. So you can consider this as how many hits we would expect to find with this particular score, say 1,446, if we were to throw a random amino acid sequence of our query length against a database of the same length we're querying. So the lower the number, the lower the E value, the more significance we assign to that. In other words, the fewer times we would expect to find randomly a sequence of this length with a score of 1446. To calculate this expected value, or E value, we need the size of the database, the size of the query, or length of the query, and then the bit score. This is now the normalized bit score. The calculation looks like this. It's 2 to the power of the negative bit score times size of the database times the size of the query. That gives us our expect value, or E value. E value allows us to assign a significance to this. It allows comparison across different queries and databases, and it puts the score itself into perspective, to a broader perspective. Okay, what does an E value of 0 mean? We talked about this in class, but just to go over it again, there is no such thing as a probability of 0. What the E value of 0 indicates is a number so low that the computer itself can't encode it properly. And so by rounding off, it becomes 0. For our purposes, we can think of those as extremely significant events. But it's important to remember that that E value is never truly 0. It's just so low that the computer rounds it to 0. We can also convert that E to a probability. What we're interested in here is finding any number of hits, or HSPs, with a score equal to or greater than the score of our match. So what's the probability of finding 1 or more, or greater than 0 hits? Doesn't really matter if we find 1 or 2 or 3. So we've broken this into 2 cases: the probability of finding 0 hits with that score, the probability of finding not 0 hits, or greater than 0 hits. So to convert that E value, and here we're using capital E to represent the E value, lowercase e is the natural log, 2.17. To calculate a probability given an E value, given an expect value, we can simply apply this bottom equation here. That's 1 minus e to the power of negative expect value. That is a direct conversion from expect value to probability. Now, we don't often do that. And the reason we don't often do that is summarized in this graph. For values less than 0.01, the expect value and the probability, or the p-value, are essentially identical. So here I've just plotted p-value from 0 to 1 versus e-value from 0 to 10. You can see that it increases very quickly. As e-value goes up, p-value goes up. We're interested in this inset graph here, which is expanding on this small region of the larger graph here. And we can see here that the p-value, when the p-value gets to be 0.01, the e-value is also 0.01. That means that any e-value that we see that's under about 0.01, we can consider that intuitively as a strict probability. Now that doesn't hold true as we get to larger values of e. Their p-value and e-value diverge quite a bit. Okay, that's about all I want you to think about as far as the statistics of BLAST. Query coverage and percent identity tell us some important information. E-value tells us how significant our hit is. Scores tell us the goodness of fit of that alignment, but they don't by themselves indicate the significance of that. Okay, at the end of this, I have 2 slides just summarizing the different BLAST options. You can take a look at these. We've gone over these before, so I won't spend any time on them. If you have any questions about these, just send me an email. Okay, that's it for today. Thank you, and I'll see you in the next lecture.